This is a laser. I'm showing it to you over the internet, which works by shooting lasers through millions of miles of cable under the oceans. If you're watching it on a phone, that's got a laser in it too. The point is, from the dance floor to the operating theater to this little setup I've made here, lasers are everywhere, and the world would be unimaginably different without them. Cats, for one thing, would have exponentially less fun. But what exactly is a laser, and what makes it different from, say, this lamp? Well, they work in pretty different ways for one thing, but we'll get to that in a second. First off, we notice a couple of key characteristics that make laser light pretty special. For one thing, lasers produce a concentrated beam of light that can be used to deliver a very high intensity. This is what makes them useful for cutting things so precisely. Also, lasers often produce light at a very specific wavelength corresponding to a single color, red in this case, unlike my lamp, which kind of emits all over the visible spectrum. And if we jump down to the level of photons, we notice something even cooler. Photons coming out of this laser are traveling in pretty much the same direction, giving us this narrow, tightly focused beam that ends up as a spot on the wall. Compare that to something like the lamp, which has randomly moving photons, producing a beam that spreads out like this. Looking back at the laser photons, we see that they all have the same wavelength, and their peaks and valleys line up. That is, they're traveling in phase. We say that the light coming out of a laser is coherent. But how does a laser work? The word laser is actually an acronym that stands for light amplification by the stimulated emission of radiation. That is a mouthful. So let's jump into an atom and figure out what it actually means. This is an atom in its ground state, which means its electron is at the lowest possible energy level. We can change that by hitting this atom with a photon of a specific energy corresponding to the energy gap between these two shells. The atom absorbs this photon and promotes the electron to a higher energy level. But atoms don't like staying in this kind of excited state. It's not always stable. So the electron's going to spontaneously drop back down at some point and release that energy in the form of an identical photon. This is called spontaneous emission, and it's what happens in a sun, in my lamp, and in a firefly's butt. But it's not what happens in a laser. The problem is spontaneous emission produces incoherent random photons, so it's not what we use for a laser. Instead, we use a process of stimulated emission that Einstein first described decades before the first laser was even built. What he realized was if you hit an excited atom with a photon of a specific energy corresponding to a transition in that atom, it's like shaking the atom and forcing it to release an identical photon. And because the photons aren't absorbed, each photon can go on to stimulate another atom to release another photon, and another, in an avalanche of photons. This is the light amplification part of our laser. And that's basically how a laser works. If you put the avalanche inside a box with mirrors at each end, the photons will bounce back and forth and keep stimulating more atoms to release more photons. If you cut a hole in the side of that box, out comes a laser beam. And now you know how lasers work. You're halfway to becoming a supervillain. Or really overeducating your cat.